Sometimes you have lists nested within lists, like this one. Or even lists within lists within lists, like this one. Usually you can just nest some for loops and you're done. But that's not what this video will be about, because sometimes you have those nasty lists like this one. Lists like this can be nested arbitrarily deep. So what we need to do to process them is recursion. And that's what we'll do in this video. Some of the examples we are going to talk about are cloning a nested list, finding the minimum or maximum value of a nested list, checking for a specific value in a nested list, calculating the sum as well as the length and the depth of a nested list, inverting a nested list, and of course flattening a nested list. Also, you can easily apply these concepts to other recursive data structures, like binary trees for example, especially considering that the concept of a nested list is much more general than the concept of a binary tree. Okay, let's get started. There will be a lot of different examples, but all of them will have the same recursive structure. So what we can do is define one generic function. I'm going to call it list recursion, and it will do exactly that. This one will need 3 parameters. More about that in a second. So what we need to do is to check whether the actual input L, which might be in a nested list or any single value, is in fact a list or not. So if it isn't a list, it might be an integer or a string or something, then we reached like the end of the recursion, the base case. Let's do that. We use the isInstance method. List. So in that case, we want to recursively call the list recursion function for all items within the list L. So we can use a list comprehension and just say list recursion. This will be every item. Same collect function, same end function for I in L. And what we can do with that is we can apply the collect function to the whole list. And this is what we're going to return. This will make sense in a second. And the other case is that we don't have a list. So our end function will handle the base case, end of L. So as I already implied, collect and end are parameters, but both of them are meant to be functions. So we could try an example. We could define this function, and for now it's just going to do nothing and return the argument. Define another function which returns the argument, and then we can call the list recursion function and we're going to use a simple nested list. Just use the functions as parameters. And as you can see, both functions do nothing, so the result will be the same as the input in this case. But we want it to be a little bit easier to write. We want to be able to do definitions of new functions in one line. So we need some kind of interface or function constructor. That's what you could call it. I'm gonna call it deep. This one will only get the collect and the end function, and we need some default values. I'm gonna do the same as I did over here in the console with lambda function, so do nothing and return the same. And will be just the same. And this one is going to return a new function actually. So not the result, but a new function, which is going to receive the missing argument L and then return list recursion like this. And this way I could do something like test equals deep, and actually I don't have my collect and my end function anymore, but we have these default values, so we can just use deep without any parameters. And then our test is a function. So this is just to make it easier later on. Actually, the first function would have been enough. The list recursion is the one actually doing everything. As you can see, the result is exactly the same as the input for this particular test function. That already looks a lot like cloning a list. So let's switch to our example document. I already prepared this, so I'm importing the deep function from this document, and then I defined some lists just for testing purposes. So let's just call it deep clone and do the same as before. And if I run this, now I already defined the nums list, and if I did c equals deep clone, we'd get the same list. But of course I could also just write r equals nums, and that would be the same list as well, wouldn't it? But the difference is that if I were to change nums now by appending 12, you can see that r changed as well, because r is just a reference, so it's not a copy, but c is actually a copy. That's why a deep clone function might be useful. But I should mention that the same problem with references might appear in our deep clone function as well. For example, if we have dictionaries in our list. Okay, but what can we actually do with the end function and the collect function? Let's start with modifying the end function. So I'm going to define a function called deep square using the deep constructor. And the end function will square every input, like this. So if I run this, it's going to square every element in our nested list. A very similar example would be a function that takes any nested list and outputs a similar nested list where all of the elements have been converted to strings. So how did I do that? If you want to think about it for a second, pause the video, but it's actually just the same as before. The string, and this time our end function will be the built-in string function. That's it. And it works fine. Notice how manipulating the end function can never change the structure of our output list. However, manipulating the collect function can. For example, we could calculate the sum of our nested list using the built-in sum function. This way, our result will be a number. Similarly, we could write a logical function that takes the built-in any function. Let's test it with our boolean nested list. And indeed, it says true, because somewhere in this nested list, there's a true. Now let's try to calculate the minimum of our nested list. Let's do it the same way as before. It won't work, because, as it says down here, the built-in minimum function can't handle any empty lists. So we need to think about that a little bit more. Let's use a lambda function instead. Let's just use the minimum function if our list is not empty, and I'm using the if-else comprehension, and then can just check if our list is not empty using if x, assuming that x is a list. And the alternative would be, well, actually, we could take infinity now, because this way any empty list in our nested list won't change the minimum, because infinity is the neutral element when it comes to finding the minimum. Let's try it like this. And indeed, let's check. The smallest element we can find anywhere in this list is 1. Okay, I just realized that I recorded way too many examples for one video, so this will be part 1, and I'm really sorry for the inconvenience of having to click anywhere on the screen to get to the second part. Bye.